children, in this part of carbon compounds, we shall start with classification of organic compounds based on functional groups. Earlier we saw that all organic compounds have a skeleton formed of carbon and hydrogen. This skeletal part is less reactive because carbon and hydrogen are relatively less reactive elements, and this skeleton you call it as alkyl group because it is any alkane, when it loses hydrogen it is called alkyl group. For example, methane CH4, when it loses one hydrogen it becomes CH3, that you call it as methyl group. And then C2H6 ethane, when it loses a hydrogen atom it is C2H5 and it is called ethyl group. So it is generally called alkyl group and it is represented by capital R, that is less reactive. And this R, the alkyl group, determines the physical properties of the compound, organic compound. But the presence of some other atoms or group of atoms in the compound makes it more reactive, and that determines the chemical properties of that organic compound. This atom or group of atoms that determines the chemical properties or the characteristic of the compound is called functional group. So the physical properties of the organic compounds are determined by the alkyl group, and the chemical properties of the compound are determined by the functional group. Carbon to carbon double bond or triple bond, these multiple bonds also are considered as functional groups because many properties of the compounds are influenced by these double and triple bonds. Other functional groups what we are going to learn are atoms of halogens, then hydroxyl group, OH group, alcohol group, that is then CHO aldehyde group, and then carboxylic acid group, COOH, are these functional groups what we are going to learn. For example, ethane is a hydrocarbon. Its molecular formula is C2H6. When one hydrogen of this ethane is replaced by OH, it becomes C2H5OH. So it is ethyl alcohol, an alcohol compound, and it is represented by ROH. That is, R is alkyl group, ethyl group here, and OH. So ethyl alcohol. A series of organic compounds containing the same functional group is called a class of organic compounds. For example, compounds having OH group are called alcohols, and those which CHO group are called aldehydes, and so on. They all belong to a class of organic compounds. Compounds having the functional group OH are called alcohols, and they have the common formula ROH, that is alkyl group with OH group. For example, ethanol, C2H5OH. Then compounds having CHO group are called aldehydes. They are represented by RCHO. Common example is acetaldehyde. Then ketones, which have the functional group C double bond O, and they are represented by RCOR dash. That is, C double bond O has two alkyl groups attached to the other two valence electrons. So to represent two different alkyl groups, we put a dash above one R. So RCOR dash. The common example is acetone. Simplest ketone is acetone, because for the C double bond O, one side the simplest alkyl group is CH3 and the other side also CH3. So it is the simplest ketone, that is acetone. The common nail polish remover what we use is this acetone. Then next is COOH, that is carboxylic acid group, that is represented as RCOOH. For example, acetic acid, CH3COOH, we have heard of in previous year itself. Then next, ester, that is represented by RCOOR dash. When an alcohol reacts with acid, we get this ester. And to represent two different alkyl groups, we use R and R dash. Example is methyl acetate. Then ether. Ether is ROR dash. When two alkyl groups are bonded in between with an oxygen atom, then it is ether, ROR dash. Simplest is dimethyl ether. Two methyl groups bonded in between with oxygen atom. Next is homologous series. Homologous series is a group or a class of organic compounds having same general formula and similar chemical properties in which the successive members differ by a CH2 group, that is methylene group. For example, if we take the alkanes, methane, one carbon organic compound is methane, CH4, ethane, C2H6, propane, C3H8, butane, C4H10, and so on. So when you look into that, each member has one methylene group, that is CH2 group, more than the precedent member, and so they are called homologs. And this series of compounds, you call it as homologous series. And coming to the characteristics of homologous series, as I told you, each member differ from the preceding or succeeding member by CH2 group, and so the difference in their molecular mass is 14 atomic mass unit. That is, atomic mass of carbon is 12, and for hydrogen 2 hydrogen atoms, so 2, so 14 atomic mass unit is the difference between the preceding and succeeding members of the homologous series. Then all the members of the homologous series contain the same elements and functional group, and they are represented by the general molecular formula here. For alkanes it is CnH2n plus 2. And then chemical properties of the members of a homologous series are similar. Chemical properties are similar because they have the same functional group and the same alkyl group differs, but the same carbon and hydrogen are present in the alkyl groups. So chemical properties are the same, but the physical properties show a regular gradation with respect to their increase in molecular mass. And all the members of the homologous series can be prepared by a common method. Coming to the nomenclature of organic compounds. Why should we need this nomenclature? Earlier, organic compounds were obtained from natural things, and they were named from the things where they are obtained. That is, for example, formic acid was obtained from red ants, and the Latin name for red ants is formica, so it was named formic acid. And butyric acid obtained from butter, and so on. So but nowadays many organic compounds are synthesized artificially from sources other than these natural sources, so we need a common systematic name, and so scientists framed a systematic method for naming these organic compounds based on their structures. So a set of rules was formulated by IUPAC, that is International Union of Pure and Applied Chemistry, that is used for naming the organic compounds. What does an IUPAC name comprise of? That is, any IUPAC name contains 3 parts. First is root word, and a prefix and a suffix. Prefix is added in front of the root word, and the suffix is written at the back of the root word. So prefix plus root word plus suffix gives an IUPAC name. Root word, it is the basic unit and that describes the carbon skeleton. It gives the number of carbon atoms present in a parent chain of a carbon compound, and it gives the pattern of arrangement of the carbon atoms. Then based on the number of carbon atoms, the carbon skeleton, that is the parent name, is given, and mostly Greek numerals are used. Except for the first 4 names, the remaining remaining root words are Greek numerals. As we saw in the earlier part itself, carbon compound containing 1 carbon is given a root word meth, 2 carbon atoms eth, 3 prop, 4 carbon atoms, bute and so on. And next is prefix. The prefix represents the substituent group or the branch that is present in the parent chain, bonded to the parent chain. Atoms or group of atoms may be attached to the parent chain. They are called the substituents or the substituent group. That is, halogens like fluorine, chlorine, bromine, iodine may be substituent groups. They may be, so the prefix added will be fluoro, chloro, bromo, iodo and so on. And sometimes it may be amino group, NH2 group, methyl group, CH3 group, or ethyl group, C2H5 group, which may be attached to the parent chain as substituents. Next is the suffix. The suffix forms the end of the name. That this suffix itself has two parts, primary suffix and secondary suffix. The primary suffix is added immediately after the root word. It represents the nature in carbon to carbon bonding of the parent chain. If all the bonds between the carbon chain are single, then the suffix, primary suffix will be ane, that is methane, ethane and so on. If the bond between the carbon to carbon and carbon is double or triple, then the primary suffix will be ene and ine respectively. If it is double bond, the primary suffix will be ene, that is ethene, propene and so on. If it is triple bond, then it will be ine, that is ethyne, propine and so on. So this is about the primary suffix. Then next, the secondary suffix describes the functional group of the compound, that is whether it is an alcohol or aldehyde and so on. If the functional group is OH, alcohol, the suffix used will be OL, that is methanol, ethanol, propanol and so on. And if it is CHO, aldehyde group, then the suffix will be al, that is AL, that methanal, ethanol, propanol. We should be careful here regarding the spelling OL and AL. When you write, it should be clear, and the pronunciation also should be clearly mentioned. That is, if it is an alcohol, all, and if it is an aldehyde, al, to differentiate clearly. Then if it is C double bond O, then it is a ketone, and it is the suffix added will be -one after the root word, primary suffix. Then if it is COOH group, it is carboxylic acid, and the secondary suffix used will be oic acid, OIC acid. Next is IUPAC rules for naming organic compounds. You have a set of rules to make it easy to name the compounds when you follow. First is we have to identify the parent name or root word. We have to identify the longest chain of carbon atom. If it is a linear chain, no problem. Starting from left to right, you can number the carbon and find out the number of carbon atoms in the compound, and you can find the root word, whether it is 3 carbon, prop, 4 carbon, bute and so on. But when you have a substituent group, then you have to follow certain rules. If it is as in the first case, where a methyl group is attached to a 5 carbon compound, as given in the example 2 of your book, on any direction you can count it to get the same 5 carbon parent compound, whether it is linear or when you start with the branch you will get only 5 carbon compound, so it will be a pentane. But if it is as in the case of as it is in the second case, where you have the example as it is in the example 3 of your book, an ethyl group is attached to the second carbon as you see in your book. When you count it from left to right, you will find to have 6 carbon compound, that is it may be a hexane, but it should not be done so. It should have the maximum the parent compound should have the maximum number of carbon atoms in the parent chain. Instead of starting from left, it is right to start counting the carbon atoms from the substituent, from the top, what we think as the substituent group. So when you count it from top, the parent chain will contain 7 carbon atoms. So it is a 7 carbon compound, that is the root word will be hept. So the substituent group will become just a methyl group. The next rule number 2 is giving a locant number for the carbon atoms. So numbering the carbon atoms should begin as it should be closest to the substituent or the functional group. So the number for the carbon atoms you give is called as locant number. So if there is a substituent group or functional group, it should contain the least number of the carbon. So if both functional group and substituent groups are present, then priority should be given to the functional group. If the carbon compound, organic compound, is an alkene or alkyne, then you should locate the double or triple bond, then give the number, locant number. So first you should write the locant number, put a dash and write the primary suffix, that is whether it is an alkene or alkyne. And you should remember that the bond, double or triple bond carbon should get the lowest possible locant number. Next rule is, if the carbon compound contains a functional group, first locate it, give its locant number, put a small dash and then write the secondary suffix, that is whether it is an alcohol or aldehyde, then OL or AL and so on. Then next is fifth rule, when the primary and secondary suffixes are joined, that is when you write alkane, that E should be removed and the secondary suffix should be added to it. Next rule is to identify the substituent or the substituent group. Just write the locant number of the substituent, put a small dash and write the prefix of the substituent. So these are the set of rules to be followed for naming the organic compounds. You have solved problems in your book which can be just looked into. First example, it is a 5 carbon compound chain. So the root word is pent and all the bonds between the carbon are saturated, single bond. So it is the primary suffix is ane, so the compound is pentane. In example 2, the longest chain contains 5 carbon atoms, so the root word is pent, and the substituent is a methyl group and it should be attached to the, it should contain the least locant number. So the numbering of the carbon atoms should start from the left, and so a methyl group is attached to the second carbon and all the carbon are attached with single bond. So the suffix is, primary suffix is ane. Group is methyl group, it is attached to the second carbon. So the locant number is 2. So the prefix is 2-methyl. So 2-methyl plus pent plus ane. So 2-methyl pentane. Coming to the third example, as I told you during explaining the first rule, the longest chain here starts from the top. So the compound contains 7 carbon atoms. So the root word is hept. There is a substituent methyl group, and to get the least number, the numbering of the carbon atoms starts from top. Number for the methyl group is 3. The carbon atoms are bonded with the or connected by a single bond, so the suffix is ane, and the substituent methyl group It's attached to the third carbon. So the prefix is 3-methyl. Name of the compound is 3-methyl plus hept plus ane. So 3-methylheptane. To the example 4, here also the compound has 5 carbon atoms. So the root word is pent. But here you see a carbon to carbon double bond. So the suffix is "-ene". It is an alkene, and the double bond should, the carbon chain, in the carbon chain the double bond should contain have the least local number. So the numbering of the carbon compound should start from the right. Only then the double bond will contain the lowest local number. The local number of the double bond is 1, and so the suffix is 1-ene. So the name of the compound becomes pent plus 1-ene. Pent-1-ene, pentene. We saw naming alkane and alkene. Now the next example is an alcohol. Here the example 1, the parent chain contains 3 carbon atoms. So the root word is prop. Only carbon to carbon single bonds are seen. So it is an alkane. So the primary suffix is ane. Functional group here is OH and alcohol, and since OH should get the lowest local number, the numbering of the carbon atom starts from the right. So the local number of OH group here is 1. So the secondary suffix is 1-ol. So the name of the compound becomes prop plus ane plus 1-ol. Propane, E should be removed, and a dash 1-ol should be added. So terminal E of the ane is removed, that is all. So it becomes propane 1-ol. The next example is an acid. Here CH3COOH is the compound given. Here the parent chain contains just 2 carbon atoms. So the root word is eth. All are single bonds. So the primary suffix is ane, and the compound contains COOH group, that is the functional group is COOH, carboxylic acid group. So the secondary suffix is oic acid. So name of the compound is eth plus ane plus oic acid. E of the ane is removed and it is replaced by oic acid. So it becomes ethanoic acid. You have other examples for you to test yourself. Try it and you can check it with the explanation given below.